All right, let's get started. Sorry about that delay this morning. This should be a shorter lecture though today. So last time we were starting to talk about the particle swarm optimization, PSO, which is a very sort of popular optimization metaheuristic, a little more modern metaheuristic. Wherever you'd see, say, ant colony optimization, you probably also will find particle swarm optimization. It's one of those ones that are up there, kind of simulated, you know, the GA, simulated annealing, part of ACO, or ant colony optimization, particle swarm optimization are kind of the big meta-heuristics that you see loaded into commercial optimization packages and a lot of other kind of optimization processes that people build into software often are kind of structured around them. So they're good ones to know about. Let me just get rid of this subtitle here. So I tried to give a quick kind of overview of where we're going, but let me step back last time, but let me step back a bit. So the PSO comes from Russell Eberhardt and James Kennedy. So there's for more info on the sort of first PSO, you can see Russell, Eberhardt and Kennedy, 1995. And Kennedy is sort of, you know, you see a lot of PSO variants coming out of work from Kennedy afterwards. And I mentioned last time that a lot of the motivation was in optimization of artificial neural networks. Or ANNs. And we'll talk in detail about artificial neural networks in the next unit, but it's kind of a sort of a brief idea of what's going on there for those who are not as familiar. A basic artificial neural network is just a fancy way to do nonlinear regression tasks and nonlinear and related classification tasks. And so there's nothing magical about neural networks. It's just a convenient way to organize regression coefficients and transformation functions. And so the idea behind a neural network is that you have a set of inputs. So these are just, you know, you can think of these as variables. So you have a set of input variables that map to a set of output variables. And all a neural network does is it tries to come up with an interesting way to, or it tries to find a function that maps input to output. And so you give it desired inputs and desired outputs. And if you give them enough of this training data, then it can find a way to map in between there. And the way it does that is it has a bunch of these nodes, which I can refer to as hidden nodes or hidden layers. And these nodes take into them potentially all of the inputs from the layer before them, and they can actually take inputs from their same layer, but just keeping it simple for the purposes of motivating PSO. And so imagine, and this is probably review for many of you, but sort of imagine that each one of these input nodes can be taken as an input to one of these, but those inputs can get scaled by certain weights. And so this input variable, you can call it x1, when it actually reaches this node, it could actually be weighted by something. We'll call it W. We'll say it's X1 W11, where it's like, where the first W1 has to do with this node, and then the one is coming from this input. So you can imagine that this one down here might be X1 W12. This might be actually got that backwards. This might be X1 W21. This might be X1 W31, and so on. And so you're just scaling each one of these things, and then they combine in a node here and in a certain way, like let's say it just adds all of those up together. There might be some switching function where the output of this node could be, you can imagine the simple sum of these things, or it might be the sum of these things threshold. So it might be whether these things are higher than a certain value or lower than a certain value. And so this output here is some function that I'll call A1 of all of those inputs, X1, W11, etc. So the X1, W11. And similarly, this thing is some function of that. And those go into other nodes, which do the exact same thing. And so basically, you've got weights on all of these edges. And in order to achieve a particular input to output mapping, in other words, for these inputs, I always want these outputs, then the training process is just an optimization algorithm which picks the weights. So there's a whole lot of weights potentially here. And so it's a high dimensional space. So it seems like it would be ideal for one of these optimization metaheuristics. We climb through this high dimensional space of weights. So, each one of these lines represents a different weight. And so those weights could be from anything from, in principle, you could bound them from 0 to 1, but what the heck, why not? You could go from -1,000 to a +1,000. So there's a lot of different values, continuous values you can put on these weights. There's a lot of different weights. Now, for any given input to output mapping, there might actually be a whole lot of different ways to solve this problem, and it works just as well. So it may be that there's so many weights in here that there's a bunch of degenerate solutions. So there could be like thousands of solutions that, you can imagine that I could tune up if I increase this weight, but then, there's another weight coming into this node over here. I could call it W21 or something like that. So maybe, if I scale all of these weights down and scale all of these weights up, maybe I end up getting the exact same solution out. So there's all of these sort of things where I can get very similar solutions with a wide range of decision variables. And this degeneracy is what makes these things difficult to solve with, say, a genetic algorithm. Because your genetic algorithm, it doesn't really care if it's hanging around one area of the decision space. And so it may be that it found a certain set of weights in some part of the decision space, and just by some mutation in another part of the decision space, it found very similar performing or slightly better performing weights way elsewhere, in a totally different other part of the decision space where the weights are totally different. And it ends up doing a recombination of those, producing a bunch of weights in the middle, which are totally useless. And it doesn't really, so it wastes a lot of time during exploration when it really should be kind of hanging tight to one set of weights and trying to optimize them, because there's kind of like, in this neural network mess, to give neural networks the flexibility that they have, it creates these images where you get sort of solutions that are mirrored across a wide range of space. And so it's not really beneficial for you to search the entire space. It's actually kind of beneficial to find a good set of solutions and kind of hang around those sets of solutions. And that's why, if for those of you who've done work with neural networks, and you probably use, and we'll talk about why these neural networks work so well for this, but there are gradient-based methods like stochastic gradient descent, which again, we'll talk about all this in the next unit, which use this thing called backpropagation, which allows you to train these weights in a very sort of systematic way that isn't quite as random as these optimization metaheuristics. And but even these have to be tamed with this sort of regularization approaches, where not only are you optimizing an input-output mapping, so you want to find the mapping from input to output that is close to the desired input to output mapping as possible. Not only are you minimizing the difference between this input output mapping and your desired input output mapping, but you also are kind of keeping all of the weights sort of close to each other or close to zero. And so there's these little terms that you add in addition to your loss function, where you're not only penalizing the performance of the mapping, you're also sort of structuring the weights themselves. And that helps kind of focus the attention of the optimizer so that it doesn't kind of go everywhere, because this decision space is just really ugly. So when they started looking at this, they said, well, maybe genetic algorithms or these other optimization metaheuristics would be nice alternatives to some of the gradient-based methods that people were coming out with. And this is, back in 1995. And so things are far less sophisticated than they are today. And so back then, these were smaller networks than they are today, and they didn't have quite as many of the tools that worked quite as well as they did today. So they were looking for these alternatives. And so what Eberhard and Kennedy thought is, they said, well, if you really think about this decision space, then what if instead of having a population that could be anywhere in the decision space, like in a GA, some of them here, some of them there, they're mutating locally, but then they're recombining and they're kind of jumping around haphazardly. Don't we really want more like a bird flock? Like, don't we just kind of want a population kind of hanging out in one area, and then they sort of murmuration over to another area? It's like a bunch of starlings you see in the sky. They're a big blob. They're covering a huge portion of the sky, but they're sticking together. And if one starling starts moving in one particular direction and gets kind of farther away from the flock, then the rest of them start kind of moving after it. And so they kind of chase after each other. And there's this consistency in them that gives them a continuity that maybe might be useful for searching these neural network weight spaces for decision variables. So that was kind of the motivation there. And so, around the same time as this is going on, there is, well, actually, well before that, but it's still, I think, fresh in everyone's minds. There's another set of work in the computer graphics literature. So this is just some background in so-called self-propelled particles. Or SPP. So I think it's an ACM SIG graph. And this is back about 9 years earlier, in 1986. There was some work from a guy named Craig Reynolds. And this wasn't focused at optimization or anything like that. This was focused at computer graphics and how do you build computer simulations for movies that you could have large groups of wildebeests or birds or whatever moving in a kind of a lifelike way. And a lot of this work was so at that time, it was a little harder to disseminate literature. And so there was a lot of work going on in parallel without a lot of people knowing it until afterwards. And so sometimes it's kind of unfortunate. We associate certain work with certain people, and then you find out that actually it was exactly the same work was like a couple of years earlier by somebody else who just didn't quite have the fame. And so I guess I should also mention there's a bunch of different things I could mention, but like this is very similar to work of like Aoki, 1982, I think, if I got that right here. And then several others. I mean, there's even some work going back to 1976. Yeah, I could list all of them here. I'm not sure, but Aoki's one that I think is often forgotten, and it is sort of at least worth mentioning. But regardless of all that, what I'm about to say is largely attributed to Craig Reynolds. And so what Reynolds wanted to build is simulations of so-called bird-like agents for computer graphics. And he called these bird-like agents boids. And that boids is like bird oid, where oid is like. So you often hear about these called the boids model, or you draw some boids or whatever, and that refers to this type of motion model. And basically a bird oid or a boid is just some agent that you draw that has that's say moving in a particular direction. So it has an angle, an orientation, and it has some perceived distance around it. So I'll kind of draw something like this. So there's some sort of distance. And what all agents in a region do, so what Reynolds defined as 4 such agents, if you put a bunch of them in a 3D simulation together, then he set up a certain set of rules where for each agent, it would maintain separation to avoid collision. It would try to align to average heading or orientation. And it would be pressured to, it would have cohesion toward average position. And these would sort of form 3 pressures, and the actual motion rule would be a weighted combination of these. So basically each agent would calculate its distance to all of the other agents around it. And then based on those distances would, that would generate sort of a force that would be away from all of each one of those agents. You could sum up all those forces. And then each one of those agents would also look at the average orientation of all of the other agents, and that would set up a force that would cause it to turn toward that average orientation. And then each one of the agents would know the average position of all of the other agents, and that would set up a force that would move them toward that average position. And then you could combine these things together. And by weighting these in different ways, then you got different flocking patterns. And so these boids ended up being very powerful in movies and things like that, in sort of being at least the first order models of large groups of things that were moving together. And then you could kind of perturb them in each way. So there were degrees of freedom that you could play with here. And they generally looked lifelike. He wasn't saying this is what birds actually do, but he's just saying that you could get these sort of, starling murmuration-like patterns out of these things, doing with these sorts of things here. So it's all just sort of kind of based on computer graphics. Now, when you look at some of these things, there are sort of optimization-like, optimization-oid things here, like the fact that they're all trying to achieve agreement on a particular position, and they're all trying to achieve agreement on a particular alignment, you could imagine them sort of minimizing some energy function here. So there's already sort of some feel of type of an optimization pressure. It just isn't kind of made explicit. So that's the first type of model that you often hear about associated as kind of inspiration with the kind of particle swarm. The other big model that people kind of view as influential in this area is the so-called Vicsek model. So this is from computer graphics, the boid model, and this is kind of written out kind of in an algorithmic format where you kind of the way that you calculate each one of these, you combine them together, and to generate these 3D agents moving around. The other one came from kind of the physics literature, and there was sort of an influential physicist in the kind of complex systems area, in the kind of condensed matter physics, those types of people. And this was Thomas Vicsek et al. It was 1995. So this is not computer graphics. This was more kind of physics oriented. And he said, imagine if you had a system of similar agents to the boid agents, where each one of them has a position in space and an orientation. So I'm going to say they've got a position, which I'll call R, which is a vector. So they've got a position in space. I'll call it Ri at any particular time. And then they also have an orientation, which I'll call theta I t. And then so we can describe their motion by this kind of simple set of difference equations, where the next orientation is just going to be the average orientation. So I'm going to use these angle brackets to denote average, taken over a neighborhood where of other agents who are less than a particular distance away. So I can say this here is the average orientation of neighbors within distance R. All right, so that's how you change your orientation. You look around you, you take the average orientation, somebody's looking this way, somebody's looking this way, the average is in the middle, those are your two neighbors, and that's your next orientation, right down the middle of those two. And then plus a little bit of noise. So I'm just gonna say, and then that there is going to be, just say zero mean white, or zero mean, I'll say white Gaussian noise. So the variance of that will come into play in a second. So then the other thing is then we actually got to have them thing move, and we just have it move like a so-called unicycle. And so what we do with that is we say the position at the next time point is going to be, the current position plus, and I'll just give myself a little room here, a constant velocity, v, times some delta t, which we assume is in between these time steps. And so imagine this is like discrete time samples of time. And then because R is a vector here, then we're going to multiply this by cosine the orientation and sine the orientation. And this is a so-called unicycle model. And so all that this thing's doing is taking the constant velocity and breaking it into horizontal and vertical terms. And then once that's broken up that way, then those will end up getting added to this R position. So R here is a position vector. So you can think of that as like X, Y. All right, so this is referred to as a unicycle model because it's, imagine if you're on a unicycle traveling at constant velocity, then the only thing you really have to control is your angle. And so you just turn your wheel and you're like a point particle that, that is moving at constant velocity, just changing its angle, and that's the way you move around. That's you know, so it's a unicycle. So a bicycle would be a little more complicated because you have to deal with the extent of where both wheels are, and that changes how you can turn and all these things. So a unicycle is just a common way to just model a point particle moving around. And so what Vicsek found is if you build a bunch of these agents that are just trying to align with the orientation of agents nearby, plus a little bit of noise in their alignment. And that's pretty much all they do, because this is just sort of integrating this these changes in the angle, because this is all kind of deterministic function of the angle. If you do that, then you can get a huge range of different collective behaviors out of these agents. And so this, taken together, the balance between density and noise magnitude, so I can call that, maybe I'll just say variance, produces a wide range of collective motion patterns. Collective. So if you think about a bunch of like, you know, like think about dolphins, you know, dolphins swim a particular way, but then think about gnats. Like if you have a bunch of gnats in front of you, they obviously are maintaining some cohesion with each other, but there's not like, you can't see continuity, like they're not kind of sort of, you know, moving around smoothly like starlings do. And you can get both of those out of this one model. So with these 2 degrees of freedom, density, you know, how dense things are, and this noise variance, then you can get all these different patterns. And as they're swimming through space, the density is going to change. And so you can get then sudden emergence of other patterns. So there can be temporary, you know, transient patterns that once the density goes down, then the new patterns emerge. And then that might create aggregations and then creates new patterns. And so there's a lot of interesting motion patterns that you can get out of this thing here. But again, you see there's this focus on alignment where your agents are trying to somehow minimize kind of an energy function. There's a tension between them that's generated up by them being out of alignment, and they're constantly trying to like minimize that energy. So there feels like these might have some sort of optimization tie-in there. And so since Vicsek and Reynolds, then a bunch of other people have added in other things. You might know of somebody who's frequently they frequently talk to him on, you know, NPR and others. So whenever people talk about collective behavior in the news, there's a guy named Ian Cousin, who's a guy who runs a Max Planck Institute right now. And Ian, back in 2002, had a similar sort of model where it's kind of, imagine the Vicsek model, but you add in not only, this is kind of a neighborhood of alignment here, but you can imagine in adding in additional neighborhoods for repulsion and in other neighborhoods for attraction. So all agents that are far away from you, you get attracted to. All agents that are really close to you, you get repelled from. And agents in the middle, you try to align. So you can imagine modifying this to have those 3 different regions, and that gives you even more flexibility in designing these patterns. And Ian would use that to model different animal movements patterns that he would see. Vicsek wasn't necessarily directly interested in that, but Ian was interested in sort of building kind of more realistic models of what rules might be going on when you have these animals moving around. So this is kind of the background of what was going on. when particle swarm optimization came out. And so particle swarm optimization said, well, let's figure out a way to turn this this apparent tension where these things are trying to be near each other as somehow a force for exploration and exploitation, where agents are going to need to want to stay together, but they're also going to want to try to follow gradients externally. And so the basic idea behind particle swarm, so the original particle swarm, functions like this. You start out and you initialize an array of particles with random positions and velocities. Random positions and velocities in a d-dimensional space. And D here is I'll say decision variables, the decision space. So this is similar to bacterial foraging optimization. All right, maybe before I go on, are there any questions about any of these motion models? It's pretty clear that so far these were not models that were used explicitly for optimization, but they were sort of the state of the art in modeling how you get these spatial patterns that were kind of influential in thinking about how you might then build flocks that swim over decision spaces in the hopes of finding good solutions to neural networks that were, it's sort of a more productive way to look over this kind of neural network space. And now PSO is used for a lot of other problems too, but it was kind of motivated by the initial incompatibility between the simple GA and the neural networks. Questions online? I don't see any in the chat. Okay. All right, so we initialize array, random positions. So then we evaluate our objective function. And by the way, this is going to be for minimization. So evaluate our objective function on all particles. Then we compare each particle's current evaluation with its personal best, and then, if necessary, update its personal best. So I'm going to call this the P-best step, personal best step. So compare each particle's evaluation with its personal best, and we'll call that P-best, and update if necessary. So that's a little bit of memory. Every particle knows the position and value of its personal best. So this is where I was, and this is how well I was doing, how low the optimization objective was there. And every particle knows its current position and its current value. And then we, the fourth step is we do the same sort of thing at the global level. So this is, I'm going to call the G-best step. And we compare each particle evaluation with the global best, which is the best among all of them, and update if necessary. So that's another piece of memory we know, is that on every particle, we know their personal best and where it was. In the whole system, we know the global best and where it was. I think we know where it was. We'll see. I'm sure I write the rule here. Yeah. Okay. So, and then finally, we got the motion rule. So I'll write that on the next page. So 5 will go on the next page here. And this is the actual motion rule. And so we're going to update velocity on each particle according to a rule that looks like this. There are different ways you can write this. So the next velocity is equal to the current velocity plus some acceleration, which this acceleration, yeah, okay, I'm going to say anything about its magnitude right now, times, we're going to, I'm going to say RP times the personal best for this agent minus its current position plus the RG, and I'll define these in a second, the global best position minus the current position. So, so I think before, and I think I was hesitating before, I wrote this last time as XJ, where I said it's the current position of the one that had the global, and that's not right. It didn't make sense to me then, but I had it in my notes. But this is the position of where the global was across the whole group, and so this isn't a position of any current agent. This is the position of the global best. And then these R's here, I'll just say that RP, this is a random value that is drawn from, and you can say 0 to, some upper, so you could just make these from 0 to 1, but if you want so sometimes, think of the original version, these had programmable upper bounds. So you didn't have to be 1, it could be anything. For simplicity, you could just say these are from 0 to 1. I'm going to write this with, I hate adding extra parameters. I'm going to write this as having kind of like an upper bound for personal best. Maybe I'll make that clear. It's a U upper bound for personal best. And this is RG is drawn from a uniform distribution, an upper bound for global best. And so every time through this, then you're going to weight the personal best and the global best differently relative to each other. And in other versions of PSO, sometimes they make these things add up to 1. So really what you're doing is you're taking a different weighted combination of these things. If you don't make them add up to 1, then you're kind of adding some gain to the whole term as well. So it sort of has like a random scaling effect as well. So here they're not being added up to 1. So you're not only kind of changing their relative values towards each other, but you're also changing their relative strength relative to the velocity, the current velocity, sort of the inertia. So in this A term here, manages the inertia. So this sort of manages inertia, where in this case, if low A means high inertia, high A, low inertia. And by inertia, I mean the tendency to keep moving in the same velocity. And so this is basically a sensitivity to social information, or sensitivity to changes from LBEST and GBEST. So if it's large, it's very sensitive. If it's small, then this thing will explore anywhere. Okay, and there are other ways, again, you can write this. So for example, other versions write this where they move the A over effectively, where they say like VI t plus 1 is equal to some, we'll say omega times V I t plus everything that's in the that above. And so this is just sort of a rescaling where instead of putting a 1 in front of your previous velocity, and then here this is usually taken as omega less than 1. So here, this is a true kind of inertial parameter. Where if you bring the omega down to 0, then you kind of don't pay at all attention of your previous velocity. You can go anywhere. If you bring omega up to 1, then your current velocity has just as much weight as anything that's in the parentheses. So there's different ways to write these, but with some scaling, they all end up being pretty much the same thing. So that's how you update the velocity. And then the last step is updating the position according to this velocity, which is, I'll write it, but it's just going to be adding the velocity to the position. So any questions about the velocity update rule? Yeah. Well, so I guess if you happen to have, it's going to be rare in particle swarm optimization for there to be two peaks very close together with kind of exactly the same values. In that very, very rare kind of pathological case where there would be two positions that have exactly the same function value, considering we're usually talking about continuous spaces, then I think you can make a non-deterministic choice. It doesn't really matter like which position you go to, but everyone's going to agree on like that's the global best. Yeah. A is constant. So yeah, this is a, in this version, this here is a hyperparameter. And so it's constant. And likewise, these upper bounds would be constant hyperparameters. And I think those are the only parameters out here, yeah. Yeah.
Similar to the other question, would we say that this is a single objective algorithm, and is there a multi-objective version?
Yes, yeah. So, so sort of note, search, or actually, I think I might have posted in the unit. I think I might have 1 or 2 articles that I've posted on multi-objective PSO. There exists multi-objective PSO or Mo PSO, but this is single objective. So you can take a look at how the multi-objective PSOs work. It's a little bit outside of the scope of what we do here. That'd be a great, if you wanted, if your final project, that would be, an algorithm that I don't cover in class, but you definitely would be open to. So those of you interested in how multi-objective particle swarms might work, maybe consider that for a final project. But I think I've got an article posted on it, so you can kind of get an idea of how they basically work. Yeah.
In the beginning, you said this was minimization.
Yeah.
What would you have to do to make it maximization?
Oh, right. Well, I mean, I guess I haven't really done anything that's special to minimization here. The original particle swarm optimization was written in terms of a minimization problem, but I mean, because only the position is kind of loaded in here, like, what we're calling what we're calling the optimum doesn't really matter. So like, if you change this to maximization, it wouldn't really affect anything here. You just like now the local best and the global best would be determined on whether you're higher than your previous one. So I guess if you look at the original Eberhardt and Kennedy paper, where they probably write out the pseudocode, they, I think, probably have a section where when you're comparing to the global best and the local best, that comparison to update the global best and local best is, is specific to minimization, which I think is the reason I have in my notes to write down for minimization. But given that I've glossed over that detail, there's nothing I've written here that would make this, you could just do it as just well for maximization. And likewise, for any minimization problem, you just put a negative in front of the optimization objective, and minimizing the negative objective is the same as maximizing the objective. And other questions on that? I haven't seen anything pop up in the chat. And I just want to make sure that I didn't miss at one time these two chats weren't in sync. So, all right, good. All right, so this is the main guts of PSO. And so now that we've updated velocity, the last thing we have to do is update positions. And to update positions, you just set the next position equal to the previous position plus the velocity. I'll say velocity, yeah, because you've just updated the t+1, et voila. And then the last thing you do is loop back to step 2. And you can do that until termination condition. And what like how do you build a termination condition? As with any metaheuristic, it's kind of up to you. So here you could say, well, let's look at the GBEST. When's the last time we updated GBEST? Well, if it's been 100 steps and GBEST hasn't been updated, then maybe this is the best we're going to do. So you could say like a number of steps, the GBEST has gone without change. That might be a good termination condition. But you could imagine lots of different termination conditions. It could just be based on the number of steps. So that's a fine thing to do as well. All right, so that's canonical PSO. And I just want to point out a couple of modifications to PSO that kind of show you other directions that this has gone in to sort of improve the performance of PSO, but they all kind of have the same sort of flavor, where it's this kind of velocity update rule, where it's, again, sort of inspired by some of these motion rules that are meant to kind of describe like bird flocks and fish schools and things like that, where you're looking at the agents around you and you feel a pressure toward maybe some central area, some global best that you're all trying to get back to, sort of an area of safety. But then likewise, you also know your personal best. And so it's almost like an individual fish knows where food is and it's hungry and it wants to go there, but it also wants to stay close to the rest of the fish, because if the rest of the fish are over there, then there's probably a lot of food over there too. So you might have found food locally, but heck, if I found food here and they're all over there, well then they must have found a lot better food than I found. And so I can locally exploit, but then I kind of always keep them close enough so that I can then go over there. And so it's kind of this idea that maybe these local rules, where you're kind of following a local gradient while also maintaining cohesion, would be enough to describe a motion rule that would be bird-like, boid-like, that would allow you to search through these weird, like neural network-like spaces. So any questions about the canonical PSO? So the way PSO would be applied the question was, how would you actually apply this to neural networks? So if I go back here, the positions here, yeah, so this d-dimensional space, these would be your, let's say your neural network had 1,000 weights. Well, then D would be 1,000. And each position in this 1,000-dimensional space would represent a different neural network. And so as you move from one 1,000-dimensional point to another 1,000-dimensional point, you've instantiated a neural network with these weights, now with these weights. And so every time you you move to a different point, you evaluate a loss function, which would be like, take all of your test cases that you know, like here's all my inputs and all my outputs. So I have a 1,000 inputs and 1,000 outputs matching to each one of those outputs. I'm going to now calculate each one of my 1,000 inputs with this neural network and see what 1,000 outputs it produces, and then measure the difference from my desired outputs, square all those, add them all up together, and that's my loss function that I'm trying to minimize. And so, so at each point, I can say, how well of a function approximator are you? And then so I've got maybe 100 particles, and that's, so at every instant, I've got 100 neural networks competing with each other, kind of attracting each other towards each other. Does that make sense? Okay. Any other questions about the canonical PSO?
The sense of what you're explaining, that would essentially be like, you said they're competing against each other to find the best weights, or the best weights for the network.
Right. Yeah. Yeah. And I should be careful about using the word compete, because it's not an evolutionary algorithm. It doesn't have that sort of flavor where we're killing off ones that aren't doing very well. But the ones who aren't doing very well will never be LBEST, and they'll certainly, well, they'll have their own. Sorry, they'll have their own personal best, but they'll never be the global best. And so the ones that aren't doing very well might tend to want to stay close to where they are. But they're always going to be pulled towards the global. And most likely that's going to cause them to diverge from where they were enough that they're going to find a better network. And so there's going to be very little keeping them. So they effectively, it is a little bit like evolutionary, where it's kind of like, really it's almost like points in space are competing with each other. And the particles are like judges or a jury that are evaluating those points in space. And so you've got 100 jury members, and each one of them saying like, this is what I feel over here. And, you know, and the rest of them, you know, so they're all kind of calling to each other in order to find the best point in space. So they're not competing, but they're sort of just cooperatively searching, if that makes sense.
This is a realistic thing. In my head, it seems like that'd be very inefficient memory-wise to have all these different neural networks performing the same problem and finding the different weights. What would be most efficient?
Right. Well, I mean, so this goes along with like, I mean, think about the GA. It's the same sort of thing. That like, if we want to optimize a neural network with a GA, each genotype would itself be, you know, 1,000-dimensional neural network. And if we want to evaluate 100 individuals in the GA, we have to do the same sort of math. And so if we're already going down this metaheuristic route, then that means we've already accepted the possibility of evaluating, you know, 100 neural networks in parallel. And neural networks aren't, I mean, they are costly to compute, but they're not that bad. And so, and you could say, well, like, well, and what would be the alternative? And so there are, again, we'll go into gradient-based methods, but these population-based methods hopefully will take fewer steps than a non-population based method. And so I guess the thought is that if you did a gradient based method, it might take you 1,000 steps of your gradient based method, but maybe if you have 100 agents working in parallel, it'll only take you 10 steps, you know? And so because you're kind of taking the effort in time and you're merging it over space. So it looks like it's a lot, but if you think about it, like the PSO is pretty nimble in terms of memory. Like, I mean, I only have to keep track of, you know, I have a little bit of memory on each agent, and I have a little bit of memory on the team, but there's not like a whole lot of memory overhead with these PSOs. And I have to keep track of where each one of them are. So again, there's like a coordinate, there's all of those weights. But you know, again, relative to other optimization strategies, it's going to be on par or even better than that. Yeah.
Exploration versus exploitation in some variants. So, like for example, like you might want them to be more random initially.
Right. So there's a question of exploration, exploitation, and managing it here, and I'll get to that in just a second. But sort of as a spoiler, this hyperparameter here. And actually, if you go in, like, let's say if you go into MATLAB, you can go into MATLAB and type help particle swarm. And you'll see MathWorks' implementation of particle swarm optimization, very similar to this one, but their parameter here, their version of this parameter, it changes its value as you go. And basically, it looks at the global best and how often the global best has been updated. And if the global best hasn't been updated very often, then it changes the inertia to maybe do a little bit more exploration. If the global best has been updated a lot, then it changes the inertia to do a little bit more exploitation. So you can make the swarm more and less sensitive based on how well the swarm is doing. And that gives it kind of this reinforcement learning type feel where they're kind of searching everywhere and then they find something and then they exploit. And then, but once they've kind of exploited enough and can't really get any more out of it, because they remember where it is, they can go exploring again. So then they go exploring a little bit more. And so it's like having these adaptive resets where once you get to a what might be a local trap, then it allows you to like kind of like these flash expansions where like you know there are certain fish or whatever that if you like scare them, then they like have this like flash expansion and then they come back together. And it's kind of like that where you can when every time you get to like a local minimum, just to make sure you're not in a trap, then you can create this kind of flash expansion that causes them to search over again. And that's what another version of this, which I'm about to talk about, we'll get into if we get there. If we don't get there, you got kind of the gist of it. So I see some questions online. So after every step, we have to evaluate the neural network. And then we do this again and again until we converge. We do it for each and every member of the flock. That's correct, yeah. And where does the objective function fit in all this? Then they say, never mind. In the second step, it's evaluated with p-best and g-best. Yes, that's a great question. Just in case you didn't catch that, this is here in these steps here. This is where the objective function comes into play. So it's super subtle. The objective function doesn't actually show up in the motion rules explicitly. It shows up there implicitly because we keep track of where the best locations so far have been. All right, so in the last couple of minutes here, I do want to mention slight modernizations of the PSO, where network effects are more focal. And so the I'm going to call this the LBEST version of the PSO, which is similar to commercial implementations of the PSO. And if you're interested, you can look up, I think it's called Particle Swarm in MATLAB. And there are Python versions of the PSO that have been implemented as well. And so in the LBEST version, we take all those agents and we place them on a communication ring. So we introduce a communication ring. And this is just a topology for purposes of communication. So what I mean by that is I want to create a neighborhood similar to the way I talked about in the Vicsek model, where you only actually pay attention to agents around you in that neighborhood. Now, in physical space, we can define neighborhood by position in physical space. But those of you who, let's say, implemented restricted tournament selection for this latest mini project, know that it's a pain in the butt to every iteration through your algorithm to figure out your neighborhood based on position and space. Because you have to ask everyone, where are you, where are you, where are you, where are you, and then calculate the position. It's not like given to you for free like it kind of is in physical space. So instead, we say, regardless of where everyone is, we're going to just say there's always a certain communication topology. Agent 1 is always next to agents 2 and 3, even if 2 and 3 are in a far-flung area of the decision space. And so now being next to isn't actually related to their position. It's just, we just assume that there's some communication topology that can be met. So you can, again, like I say, create a ring, like I have agent 1 next to agent 2, and it's bidirectional, I guess. Agent 2 is next to agent 3, goes around, and then I've got my agent N is next to agent 1. And now that I have this ring, then I can define this is like N agents organized on a ring. And now that I have this ring, then I can define a local best based on a neighborhood size. So in other words, each one of these agents knows its personal best. And so what I can do is I can replace gbest, now I'm rushing a little bit here, with LBEST. And so the idea here is that instead, so I just go back to the exact same particle swarm algorithm that I just showed you, but instead of having that X superscript G, that global best, replace that with a local best, which is the kind of best of all of the agents in my neighborhood. So I can define a neighborhood size. And so that might be, the 3 agents. And so then on the focal agent, it will ask every other agent in its neighborhood, what is your personal best? And it will take the best of all of those and turn that into the local best. And it will act like a global best just for that agent. And so this somehow allows for a little bit more exploration. So this is, if you make the neighborhood size the whole network, it just becomes normal particle swarm optimization. If you make the neighborhood size 1, then you kind of ignore how well everyone else is doing. So this parameter allows for tuning sort of exploration and exploitation. In a similar way that tournament selection has a parameter where you're either having tournaments of 2 or tournaments of n. So it's sort of like saying, who are we paying attention to? Are we paying attention to how well everyone's doing, or only the few that are next to us? So that's kind of the LBEST version. And just because the question was asked, I do want to mention that there is, I'm not going to go into detail here, but I will mention that Kennedy was looking at these versions that were coming out and actually published, and I've got a paper on it, something called FIPS, which was, I think, what does FIPS stand for? It is fully informed particle swarm. And this is just kind of a bonus piece of information. And this is also by Kennedy. And you can see the article of it online. And FIPS basically said, all right, why don't we instead just create a random we can choose different topologies, but we're going to have fully connected topologies. But then we're going to have random weights that we apply to every agent in that. And so every agent can see the personal best of every other agent, but they weight them all differently in kind of random ways. And so this becomes a fully informed version of this kind of local best. And the idea here that they found out is that you get really a lot of sensitivity to network topology, but what's nice about it is that it gives you a lot of, it does actually very well. It can actually do better than normal particle swarm, but it can, I'm trying to find my big point here, that exactly what's the parameter here. But the idea here is that this weighting, oh, that's what I want to do. I apologize for not having my thoughts collected here. Is that, well, okay, let me back up. So that so what I was trying to say earlier here, and again, I'm just sorry that I rushed myself and I apologize for getting here late. Like I said, the network size here adjusts exploration and exploitation. In MATLAB's version of this, this is another parameter that they play with to try to have adaptive exploration when things start getting stale. And so you can adjust the network size dynamically in the algorithm. You can make it smaller, you can make it larger, just like you can adjust that inertia weight. So it gives you more control over that. And this FIPS just further plays with that idea. And that's kind of all that I want to say about it. Only other things I'll mention on particle swarm optimization, practical things, is if the plain vanilla particle swarm optimization has the problem that velocities can go to infinity. So very often they add practical things like they put caps on velocity, but overall, if you were to look at like the implementation of particle swarm optimization, the modern implementations, they don't look that different from the canonical versions. Like I said, they've got this kind of adaptive restart sort of thing to make it better at finding global solutions, but overall, it's pretty much that's how it works. So that's all that I want to say about swarm intelligence. Next week, I'm going to start on neural networks, and we'll go down that path. And that's all I've got. So I don't want to keep you any longer. If you have any questions, I'm happy to stay over for those. But if you need to go, feel free to take off. Yeah, and don't worry about FIPS. All right, I saw there might be a question online, or this might be the old one. All right, looks like that was the old question. Any other questions online? All right, if not, then we will see you all, Thursday for neural networks.